Hi, my name is Rebecca Buchholz, and Dr. Wenfu Tang and I will talk today about applications of wildfire in the community Earth system model, specifically as related to atmospheric composition and chemistry. Now, the reason we're interested in wildfires and their impact on atmospheric chemistry is because a large amount of trace gases and aerosols are emitted from fires into the atmosphere, and they can degrade air quality by, for example, leading to the formation of tropospheric ozone, PM 2.5, and secondary organic aerosols. The impact can occur close to fires, as well as have transported impacts far downwind of the fire. So, for example, on the right here, we see a satellite image of carbon monoxide on September 16th, 2020, and we can see fire emissions of carbon monoxide in the Pacific Northwest being transported far across the North American continent. Now, fire emissions can also change weather properties, such as through cloud-aerosol interactions and impacts on precipitation. And there's increasing study on the two-way climate feedbacks. So climate properties can impact the frequency and occurrence of fires, and the large emissions from fires can also have a feedback effect on climate properties. There are many possible ways to use the community Earth system model to study fire emissions, and we'll talk about a few of these ways today. So this is a schematic of the community Earth system model components and how they all connect together. And the first thing we'll talk about is using prescribed emissions in the atmospheric component of the model. There are a couple of ways to create these offline prescribed emissions. The first method is to use burned area, satellite measured burned area, combined with biomass loading and fraction burned to create fuel consumption in kilograms of carbon burned. The second method is to use satellite measured fire radiative power, which is a measure of fire intensity, and combine that with biome-specific conversion factors to again get fuel consumption. Once we have fuel consumption, this is combined with emission factors that are collated from field and laboratory studies. And the combination of fuel consumption and emission factors then provides these emissions that we can read into the model. And there are a few different inventories that are created this way. In the middle here, I'm showing two of these inventories, FIN and GFAS, and I'm showing carbon monoxide fire emissions in 2014 in teragrams. And the main takeaway from this slide is that in different regions, different inventories perform best. So in the top left are 5 different fire emission inventories, and we ran these through the model and compared them with satellite measured carbon monoxide from the instrument called MOPIT. And we saw the comparison between total column carbon monoxide looked different in different regions. So different inventories performed better in different regions. And the reason there are differences between these inventories is because of the assumptions that go into creating the emissions. So these assumptions have associated uncertainties. And so, for example, land cover may have an uncertainty associated with misidentification of vegetation type, and also there's estimation of fuel consumption. Fire detection, satellites can miss detection of small fires, and also there's cloud interference in the detection of fires as well. Emission factors also have associated uncertainty, particularly for the aggregation of biomes. So, for example, tropical forests are assumed to have the same emission factor across the globe. And we can do sensitivity studies on each of these uncertainties, and below here I'm showing you a simulation experiment using emission factor uncertainties. So we create a range of emissions based on these emission factor uncertainties and then run them through the community Earth system model to create an uncertainty bound on our output of carbon monoxide. And we can see on the right here, the range of uncertainty due to the emission factor uncertainty can explain the differences between using the different inventories outside of the fire season, but within the fire season, the uncertainty from emission factors really only goes a little way to describe those differences between using the different inventories. And so these other uncertainties are also having an impact likely in this fire season. Now, even though we have these uncertainties in these emission inventories, they're still useful to use to track and trace the impact of fire emissions on atmospheric composition. And there's a couple of ways we can do that. On the left here, I'm showing an example of tag tracer studies where we tag specific sources of carbon monoxide in the model and then track where they go in the model. So in this way, we were able to attribute anomalies of carbon monoxide to specific sources. And this kind of an experiment doesn't impact chemistry in the model. It's a full chemistry simulation and uses just tag tracers. On the right here, we have an example of sensitivity studies where we use emissions from fires in the model and then also take them out of the model and compare the simulations with and without fire emissions. This can give us the impact of the fire emissions on atmospheric composition and air quality, and will include the complete chemical feedbacks in the model. So now, because the community Earth system model is a coupled Earth system model, we can also look at the impact of sensitivity studies on climate properties. And John Fasula led a study recently that looked at the difference between using SSP 245 fire emissions compared to observationally constrained fire emissions with GFED for the Australian 2019-2020 wildfire season. And what John found was the large Australian fire emissions had a really huge impact on cloud brightening across all of the southern hemisphere. And this led to a La Nina response in the model that also we saw observationally. Now we can see these climate scale impacts in the model, but there are also shorter term impacts on weather. And I'll hand it over to Wenfu now to talk about those.
Thank you, Rebecca. Here is an example of using CESM to study the impact of Pacific Northwest wildfire emissions on precipitation during 2018. So this work was done by our summer intern, Pei Hao from CU Boulder. So two simulations were conducted. The control run uses the FIN version 2.2 fire emissions, and the sensitivity run was the same as the control run, except that the fire emissions over Pacific Northwest were turned off. So this figure here shows the resulted precipitation change in September 2018. As we can see, some southeast regions experienced a significant precipitation decrease when the Pacific Northwest wildfire emissions are turned off. So, and next slide, please. So, this slide gives an example of fire studies in our new model, MUSICA version 0. So, MUSICA version 0 is a configuration of CESM. So the full name is the Multi-Scale Infrastructure for Chemistry and Aerosols. So if you look at this figure on the left, bottom left, so it shows the grid of the MUSICA version 0. So outside the refined region, it's about 1 degree resolution. Well, within the refined region, it is about 14 kilometers. So now let's look at the figure on the right. This is an example of using MUSICA version 0 to study fire plume. So the model grids within the plume are shown, along with the CO carbon monoxide concentrations and the wind at the model surface layer at 17 p.m. of August 7th, 2019, over the Washington state, this fire. So the locations of the 1-minute merged airborne observations are also shown by the black lines and black dots. So this figure indicates that the resolution of MUSICA version 0 has come down to the scale that is approximately comparable to the fire plume and the 1-minute merged airborne observations. So next slide, please. So as we know, fire impacts on the atmosphere were significantly determined by the features of fires, such as the fire diurnal cycle and the plume rise. Here I'm showing an example of using the model sensitivity study to determine the impact of fire diurnal cycle and the plume rise on the model results. So the two figures on the left shows the typical diurnal cycle and the plume injection profiles we found from the literature. So we applied these two features to the fire emissions, and that resulted in 4 simulations, as shown on the in the figure caption on the upper right part of the slide. So there's a control run without diurnal cycle or plume rise, and a sensitivity run with diurnal cycle, a sensitivity run with plume rise, and lastly, a sensitivity run with both diurnal cycle and plume rise. So if you look at the figure on the right, it shows the modeled carbon monoxide concentrations and a vertical profile of wind and also PBL height averaged over the plume shown in the previous slide. As we can see, the CO profiles in these 4 simulations are different due to the diurnal cycle and plume rise. The diurnal cycle and plume rise changes the transport of fire-emitted trace gases and aerosols because when they are emitted at different times of a day and a different altitude, they will be subject to different meteorological conditions and transported differently. And next slide, please. So all the previous examples we have gave so far mainly focus on the fire and fire emissions impact in the atmosphere component, and they all use prescribed emissions. However, as we know, fires also directly interact with other components of the Earth system, and there are also other options in CESM. For example, there is a fire model in the land component. Although currently by default, the fire emissions calculated from the land is not coupled to the atmosphere. Next slide, please. So the two figures here shows the structure of the fire model in the CLM5. So there are 4 types of fires that are parameterized in different ways, namely agricultural fires, deforestation fires in tropical closed forests, peat fires, and others. And as for the category of others, this figure on the right shows the detailed parameterization. So basically, the parameterization calculates the fire occurrence and the fire spread. And by combining the two, we can get burn area. And then based on burn area, we can then calculate the fire impacts, including the fire emissions. So next slide, please. So here I'm showing an example of future projection study of fires under different future scenarios. So we analyzed the burn area changes calculated by the CLM fire scheme under 7 scenarios. 5 of these scenarios are SSP scenarios, ranging from sustainable development to the unmitigated baseline scenario. And the 2 geoengineering scenarios are based on the unmitigated baseline scenario, but they modified the climate system through adding stratospheric sulfate aerosols or solar irradiance reduction. So this figure on the right shows the time series of global total burn area under these 7 scenarios. As we can see, the global total wildfire burn area is projected to decrease under the geoengineering and the overshoot scenarios, but increase under all the other scenarios. And the next slide, please. Yeah, it is also worth noticing that attempts are being made to couple fire emissions calculated from the land to the atmosphere. So that is a work in progress. And here are also some other potential applications we didn't cover but worth mentioning here. With that, I will thank you for your attention, and feel free to email us if you have any questions.